Hey physics peeps, we're going to translate between position versus time graphs and velocity versus time graphs. When we get into this, we want to review just few things that we've done before. One thing is that velocity and speed are usually synonymous. So we can talk about velocity versus time graph. It's the same thing as a speed versus time graph for what we deal with. That's fine. But on each of these graphs or types of graphs, position versus time, velocity versus time, we can find different things. On a position versus time graph, we can find position information or how far something went, but we can also find something like velocity, which is the same as its slope on the graph. And so we can remember that, and slope, we'd use that equation y2 minus y1 over x2 minus x1. And for the units, it's really the units for the y-axis over the units for the x-axis. There's another way that we could get that velocity though, and it's using the same thing that we've used before, where we can use that velocity equals distance over time. You'll see me use both of them in here, but you can choose which one that you want. On a velocity versus time graph, or speed versus time, we can find velocity information from it. But we can also figure out things like acceleration, which come from the slope. It's the same equation. We can also use something that we used before, like that VF minus VI divided by T equation. That works here as well. And then distance equals the area underneath the graph. And we'll take a look at that, or you can take a look at that on another video as well. Okay? So we're going to work through a few examples because translating between these graphs is a little bit of a puzzle. It's figuring out what you have first. So let's read it. And a box is being moved by a conveyor belt. The belt is programmed to move the box at 8 meters down the belt in 4 seconds. Then keeps the box from moving for 3 seconds. Sorry, there's that line, but it says 3 seconds. Then moves the box 12 more meters in 3 seconds. We have to draw a position versus time and a velocity versus time graph for that. But which one do you draw first? It really doesn't matter, but probably what makes it easier is knowing what information you were given. And when you look at it, it's split up into 3 different parts. Says what's going on in the graph, or what will be going on in the graph. And when I look at this 8 meters, that unit meters, that matches up with the position. So I could actually draw my position versus time graph first. And so if I do that, I'm going to keep track of the position and the time as we go. So it first starts off with 8 meters down the belt in 4 seconds. So for my time, I'm going to move along starting at 0, 1, 2, 3, 4 seconds. And this box moved 8 meters. So on my position, it also starts at 0. Position versus time graph start at 0. It goes up 8. So 8 ends up being right about here-ish. And I'm going to make my mark where those meet. And it is a straight line. So we assume constant speed, unless if they tell us otherwise. And so a straight line connects them. Then it keeps the box from moving for 3 seconds. So it's really stopped for 3 seconds. It's not moving, it's not changing position. So on my time axis, from where I left off, it's 3 more seconds. 1, 2, 3. And now I'm at the 7-second mark. And my position is not changing. So it's in the same spot as it was before. And then the box moves 12 more meters in 3 seconds. Keep in mind that this is 12 more meters. It's not up to 12. Okay? But I will move along the time axis in 3 seconds from where I left off. 1, 2, 3. And I have to go 12 more than where I was. So I would left off at 8, and I have to add 12 more. So 8 plus 12, I am actually at 20. And it's a straight diagonal line. And this is my position versus time graph. To draw this, now that I have that information, I can draw my speed versus time graph or velocity versus time graph. But I need the velocities in order to do it. They gave me positions or distances. So I need to solve for that. You could either do that by slope off of this graph, where you can do y2 minus y1 over x2 minus x1. And if we do that, we can take things like y2 has to be from the second point, and then you're doing it per section. So for this first section, it's y2 is 8 minus y1, y-axis, and the first point is at 0, over x2, the second point on the x-axis, it's 4, and minus x1 on the x-axis, it's 0. So you get 8 divided by 4, we get 2. And that's equal to the velocity. But I put that on here over on this side by saying that it starts at 2 for these first 4 seconds. So I go out 1, 2, 3, 4. The velocity is 4. And it's a flat line. And so when you go to the velocity versus time graphs, just keep in mind that you are changing your mindset on what it is that you're recording and how you're recording it. Its velocity is 2 for those 4 seconds. The next part, the velocity is 0. It wasn't moving. And so when you got a flat line, you know it's 0. So I can draw that for the next part. Its speed is 0 over the next 3 seconds. 1, 2, 3. And I can connect this with a straight line, do a dotted line down. And the last part is 12 more meters in 3 seconds. I can do this slope equation again, but there is that other way of solving it out. You could solve out for these speeds or velocities using this equation, and it works the same way as it would for this first section, where the distance was 8, and it did that in 4 seconds. Great, you get the same answer. If I want to do that for this section, its velocity is the distance divided by the time, but it's only for that section. So it's not 20 for the distance. It only moved 12 meters. So you could use it from the graph, or you could use it from the description. 12 meters in 3 seconds. If I divide them, I get 4. And that's the velocity for that section. So from where I left off, velocity is 4, and it happens for 1, 2, 3 seconds. And I connect them. And that's how we draw this type of graph. So I'm going to show you another type of graph here. Oops. Exit out. Where it says Ava is moving through an obstacle course. She starts by moving at a constant speed of 4 meters per second for 3 seconds, then comes to a stop for 2 seconds. Then she needs to walk very slowly at 2 meters per second for 5 seconds. And so when we draw this or these graphs, again, it doesn't matter which one that you draw first. You could draw the position versus time or the velocity versus time. But the information that they give you really goes along with speeds or velocities because it's in meters per second. So let's draw that one out first. So the velocity, it starts off, Ava starts going at 4 meters per second for 3 seconds. So 4 meters per second for 1, 2, 3 seconds. Yay. Then comes to a stop for 2 seconds. So their velocity is 0. So where I left off, the speed is 0, and that's for 1, 2 seconds. Then she needs to walk very slowly at 2 meters per second for 5 seconds. So from where I left off, it's 2 meters per second for 1, 2, 3, 4, 5 seconds. And I can connect these little pieces here with dotted lines just to say that it moves from 4 meters per second to 0 meters per second to 2 meters per second. That's kind of it. So that's what our velocity versus time graph looks like. To get my position versus time graph, though, I need to find area on a velocity versus time graph. And so area, and for rectangles, area is equal to the length times the width. So if I take the length of this section times the width of this section, I will find the distance that it went on here. So the length for this first section is 3 times the width, which is 0 to 4, it's 4. And I get 12 meters that it traveled. So over here on my position versus time graph, I start at 0, and for those first 3 seconds, 1, 2, 3, it went 12 meters. So I write that on here by going, about here is 12. And I make my mark. It's a straight diagonal line between them. And then it says, she comes to a stop for 2 seconds. Well, here the area underneath the graph is just 0 because the length might be 2 seconds, but the width is 0. It doesn't go above the bottom of the graph. So it doesn't move over those next 2 seconds. So on my time axis down here, I go 1, 2, and I am in the same spot where I left off. I'm still at 12. For my third spot, I take the length, but keep in mind that it is not 10. It is going from here to this spot. So 1, 2, 3, 4, 5, because it lasted 5 seconds, times the width of 2. I get 10 meters. So this next part, keep in mind, it does not go to the 10 meter mark. It goes 10 more meters. So from where I left off at 12. When I go 5 more seconds, 1, 2, 3, 4, 5 seconds, that it goes up 10 meters further. So plus 10. I'm really going to be at like 22 right here. It's a straight diagonal line. And that's how I draw my position versus time and velocity versus time graphs. You choose the graph first that matches up with what information that they give you or what information they want, and then you can draw the other one. If you are given position versus time or position information, use the speed equation to solve for velocity, or velocity equation to solve for the velocities. If you are given velocities, you can use, close this. If you are given velocities like here, you can find the area underneath to solve for the positions, and then you graph it out. So that's kind of how you go through those problems. There are some other types of problems where you can be given a graph, but then you need to draw the other one. And you could do it in the same way, where maybe they might have you fill out a description for it. Like here, they have blank meters per second for so many seconds. You're doing the same thing. You're just looking for meters per second. Oh, those are speeds or velocities. You have to find that on this graph. So you have to use something like V equals D over T to solve out for that speed or slope. Either way, it works. And so that's kind of how you go through those. Let your teacher know if you have any questions. You guys have been doing an awesome job. We'll talk to you later. Bye.